So solver-aided programming is on the rise, and a common way for programmers to get a solver to help with tasks such as testing, verification, and synthesis is to use symbolic execution to first compile a program into constraints that the solver can understand. But a challenge for symbolic execution is to support a lot of program features because that enables more application, makes it more useful. But the cost of supporting some program features is that it can produce harder to solve constraints. For example, data structures, if you try to symbolically execute lists or sets, symbolic execution can produce very large and complicated constraints. So the Rosette language has found a nice compromise to this tension between features and constraint difficulty. Specifically, Rosette is able to keep constraints relatively simple, but at the same time it supports many of the features that programmers actually want to use. And so as a result, Rosette users have been able to deploy it in a variety of real-world applications. So how does it achieve this? First, in order to keep constraints simple, Rosette equips only a small subset of a language for symbolic execution. Rosette uses Racket as its host language. But then, to allow programmers to use more features, Rosette does two things, which is the first is that it uses macros to build more complicated abstractions on top of the small core. And so Rosette programmers frequently use it as a framework in which to build solver-aided DSLs. And the second thing that Rosette allows, it allows programmers to combine unlifted features, unlifted code with their symbolic code. And so programmers can actually use all of Racket with the Rosette language. So in our paper, we call this style of computation lenient symbolic execution because it allows you to pull in non-symbolic, non-lifted features. But this kind of mixing of symbolic and concrete execution can be problematic sometimes because the programmer is left to manually make sure that they're using symbolic values correctly. So our contribution is to help programmers with the type system. So we created Typed Rosette, and Typed Rosette's type system will automatically make sure that the programmer is not using symbolic values where they're not supposed to. Okay. So is this better? Sorry. So here's an example to demonstrate what I'm talking about. Let's say that I've invented a new sorting algorithm. If I implement it in a traditional language such as Racket, I might write tests, but tests are imperfect. So in Rosette, what I can do instead, if I switch to the Rosette language, I get these new identifiers in blue. Instead, I can define symbolic values. So here I've defined three integer symbolic values, x, y, and z in red. And then I can call a solver. That's what this verify function is doing. I can call a solver to verify my assertion here that calling my new sort algorithm with any list of length 3 will satisfy this sorted predicate. And so here the solver is unable to find any counterexamples to my assertion and confirms that my algorithm is correct. So what does it mean to be correct? Well, we just use the standard property of sorted lists, where if you have two elements of the list at indices I and j, if I comes before j, then the element at I has to be less than or equal to the element at j. And we can again express this with symbolic values. And finally, assume that this is my new sort algorithm. If you go and try to read it implemented this way, maybe it's a little bit hard to read. So I've implemented it a second way. Now it's split up into two functions. But the interesting part is that now I'm pulling in another library, which Rosette allows you to do that implements pattern matching. So I'm adding I like using pattern matching, so I'm just going to add it. And so my sort function now pattern matches on its input. So if it sees an empty list, returns the empty list. If it sees a non-empty list, then it calls the second helper function, and the second helper function is structured similarly. It also uses some guard cases. But the important part is that even though I've pulled in this new feature, the solver is still happy and still confirms that my algorithm is correct. Okay, so some of you might have figured out that my sorting algorithm is actually just insertion sort. So let's say I find a list library that is already implemented this insert function for me, and so I go ahead and I just use that. But now the solver output has changed, and it's no longer happy. It returns a counterexample that supposedly my algorithm doesn't work at. But now I'm confused because if I apply my sort function to the counterexample, it actually returns a sorted list. And so if I'm a programmer now, I don't really know what to do. I don't know where to go to look for the problem. But given the way I've structured this talk, maybe you've guessed that the problem is with the insert function, and that's indeed the case. The problem is that the insert function is written using parts of the language that don't support symbolic execution, and so it expects a concrete input. But here I've given it a symbolic input, a symbolic value. So if I rewrite my example using types instead of a solver output that I don't really understand, here now my typed Rosette language points out the exact cause of the error with a nice type error message, which is that I've given insert a symbolic value when it should be concrete. So our typed Rosette language is based on a core symbolic lambda calculus that supports higher order functions and mutation. And for types, we have, for now, for this talk, I'm just going to assume that we have base integers and function types. And then as a first step, we add symbolic values and symbolic types. So symbolic values are written as variables with a hat and a type annotation, and symbolic types are written as just regular types with the same hat. And so in my calculus, I would write a symbolic int, as you see on the screen, and it would have a symbolic type. I should note that the symbolic type actually represents possibly symbolic values, and so our calculus uses subtyping, includes standard subtyping rules, and so a concrete type such as int without the hat is a subtype of the possibly symbolic integers. And so a concrete value such as 5 can have either a concrete integer type without the hat or a symbolic integer type with the hat. So it turns out that just what you see here is good enough to make sure that symbolic values don't go to where they're not expected. But it's not good enough for our language because it also rejects many of the programs that we would want to write. So here's an example to show what I mean. What type should we give the add1 primitive function? We want it to support symbolic values, so maybe let's give it a type of symbolic integer to symbolic integer. But then if we apply this function at a concrete value, then that expression itself now has a symbolic type. And so we're unable to pass this value or this expression to a concrete function, which largely defeats the purpose of lenient symbolic execution. And so the problem here is that the symbolicness in the types has spread too quickly, and so we also want our type system to do something about this. And so to summarize our goals, we we of course want our type system to be safe. We want it to prevent improper use of symbolic values, but it also has to be useful. It also has to allow us to write the programs that we want, and the way that it does it is that by preserving concrete types as much as possible. So for this talk, if you're interested in the safety part, you can read our theorem in the paper. But for this talk, I'm going to focus on the second aspect, which we achieve using something we call concreteness polymorphism. So concreteness polymorphism has three components, and I'm going to talk about two of them. The first is intersection types for functions. The second is path concreteness markers. And the third is union types and occurrence typing. So first I'm going to show how function intersection types help us to achieve a more useful type system. So here I've just extended the types with intersection types. And what this allows us is to assign a function like add1 a type of concrete int to concrete int intersected with symbolic int to symbolic int. So now, using the standard rules for intersection types, if I apply add1 to a concrete value, that expression will preserve its concrete type. But at the same time, I can still use add1 with symbolic values, and that expression will properly be assigned a symbolic type. All right, so now let me talk about the second part. And I'm going to explain it with an example. So imagine I have a program and I define a variable x that has an initial value of 0. The type system will assign x a concrete type because 0 is a concrete value. And then I can mutate x with other concrete values. That's fine because, for example, 3 here is also another concrete value. But now, let's say that I define a symbolic Boolean, and then I have a conditional that branches on this symbolic value, and each of the branches of the conditional also mutates x. Now, since the test of the conditional is symbolic execution will evaluate both branches. So the result is that x will be a symbolic value that's either 10 or 11. But the problem, of course, is that x has a concrete type, which means that we can pass it to functions expecting concrete values, and so this is unsafe. But we can't just reject mutation, because there are some cases that we can't just reject mutation of concrete values, because there are some cases that we want to support. So again, in order to make our type system more useful for the programs that we want to write, we track the type system tracks the concreteness of the path. So we do this with two kinds of path markers, denoted with a black circle and a white circle. So the black circle represents concrete paths, and the white circle represents possibly symbolic paths. For those that are familiar with information flow type systems, this is very similar to the PC marker that is used to track implicit flows. And so with these path markers, now we can define type rules that depend on them. So here's two parts of the type rule for if expressions. On the left, the if expression occurs in a concrete path because it uses the black circle judgment. But since the test of the if expression is also has a concrete type, we can type check the branches of the if using the same concrete judgment with the black circle. But then on the right, since the test is symbolic, then we have to change to using the symbolic path judgment denoted with the white circle on the right. So now, with this setup, we can define the mutation rules that we want. So on the left, if a mutation occurs in a concrete path, then we can do the usual thing. But on the right, if the mutation happens in a symbolic path, then we restrict it to only mutating variables that have a symbolic type, since the mutation can change the variable to a symbolic value. Okay, so we're not quite done yet. Here's a similar example where I define x to be 0, but instead of mutating it directly, I have a function f that mutates my variable x. So the question is this safe to do? And the answer is it depends. It depends on where I call f. So here, if I call f in a concrete path, then that's okay, because because x is still bound to a concrete value. But if, like before, I call it in a symbolic path, then now again it becomes bound to a symbolic value, and has a concrete type, which is unsafe. And so the interesting part is that now it matters where I call the function rather than where the set expression is. And so we need to add a little bit of context sensitivity to our type system as well, because we want to allow some cases, but we want to reject other cases. And the way we do this is we add another component to function types, which is a path, and this indicates the kinds of paths under which the function is allowed to be applied. And we can see that in the application rule. If we're applying a function in a certain path pi, then the function must have a type that matches the context of the application. And then for function definitions, we can ignore the path of where the definition is, and instead we type check the body of the function twice, once assuming a concrete path and once assuming a symbolic path, and then we assign a type, we assign the function a type for all of the valid cases, or an intersection of multiple cases, if that's the case. Okay, so very briefly, I'd just like to talk about the implementation of Typed Rosette. Typed Rosette is implemented as a series of abstraction layers. So at the bottom is Racket, as well as the solver. Rosette uses Z3 by default. And then on top of that, Rosette is implemented as language extensions of Racket. So it extends Racket with symbolic values, as well as an API to the solver. And as I mentioned previously, Rosette is split into two parts, a lifted part where everything supports symbolic values, and an unlifted part that has more features but doesn't support symbolic values. And then on top of that, we implemented Typed Rosette as syntax extensions of Rosette. And that includes the type checker, which we also implemented as syntax extensions, and we did that using the type systems as macros approach that I developed with my co-authors and presented at POPL last year. And this approach allowed us to completely reuse the implementation of Rosette without any modification. So very quickly, this implementation style allows us to implement type rules using a declarative syntax that looks like the type rules that language designers already write. So here's the set type rule implementation that I just pulled out of our source code, and it has two clauses. And I'm not going to get into the details, but hopefully you can see that it pretty much exactly corresponds to the mutation rules that I presented earlier. And finally, I mentioned that we want our type system to be useful. So how do we know that it's useful? Well, we ported several projects from Rosette to our typed language, about 10,000 lines of code and another 6,000 lines of tests. And here's a snippet from the table in the paper. And what I'd just like to briefly point out is that the table includes the size of the original project as well as how many lines we had to add to port it to Typed Rosette. And these extra lines of code include annotations and function signatures, type annotations for function arguments and type signatures. In a few corner cases, we had to add some casts to help the type checker. But also, since Rosette programmers frequently use it to create new language forms, in several cases, we had to extend our type system with new type rules to support these features. But the implementation style that we used made this pretty straightforward. Okay, so to conclude, Rosette supports lenient symbolic execution, which produces relatively simple constraints, but allows programmers to write programs using the features that they want. The one catch is that writing programs this way can be hard to debug, and so we introduced Typed Rosette, which automatically helps programmers make sure that they're using symbolic values properly, but it also allows them to write the programs that they want to write using concreteness polymorphism to preserve the concreteness of as much as possible. So if anyone's interested in trying Typed Rosette, the easiest way to do so is to just install Racket, and then you can install Typed Rosette from the Racket package manager using the line at the bottom of this slide, and that will install Z3 and Rosette and all the dependencies automatically. Thank you.
Thank you very much. So we have time for a few questions. Begin with one from online. And it says, can the type system be used to verify non-interference by having all public variables concrete type and the secret variables be the symbolic type, and then type check at the end whether we have any public variables that are symbolic?
Right. So I think that it probably cannot, because it I'm not sure. I think the labels that we have are probably not expressive enough to express in the type system.
Okay, thank you.
Yeah, so I'm also interested in this relation with information flow type systems. For example, you had this type for functions with a sort of symbolic or
right.
concrete marker. So that strikes me as similar to the kind of effect type that you have in these information flow type systems of the level up to which they write.
Yeah.
So can you interpret your type system as a kind of instance of an information flow type system, or is there a difference?
So I think there are similarities. I think the main difference is that in information flow systems, the label checking is mostly independent of type checking. Someone correct me if I'm wrong, but in our type system, these quote-unquote label checks are more interleaved with the type rules. For example, to check an if expression, we have to check that whether the test is symbolic and whether it has a certain type. And then, in addition to that, I think to summarize, it's that our type rules need to inspect the labels more than in information flow systems. And then on top of that, the programmer, I didn't get to this in the talk, but the programmer also needs to be able to inspect the labels. So for example, to implement a function with the intersection types, so for the programmer to be able to implement a function with this type, they have to be able to write code that says if the argument has label symbolic, then call function 1, otherwise do function 2. And so you have to be able to inspect the labels and dispatch to different pieces of code.
Other questions?